Share. Okay, now let's try it one more time. Sorry, just I had the kids all yelling in the background, so I'm a little distracted. Okay, now, first choice, the first choice C here is correct. Of course, the choices are scrambled for every person who takes this test. So if you don't have as much mass, obviously you don't have as much momentum, right? So remember, momentum is mass times velocity. So if you keep the velocity the same, then the mass is directly impacting the momentum. So more mass, more momentum, less mass, less momentum. Remember, joule is the unit for energy. Energy is force times distance. Force is in Newton, and force is mass times acceleration. So you definitely need the kilograms. Acceleration is meters per second squared, but you multiply by meters again, that's what you get the meters squared. For number 3, remember, power is energy over time, or work over time. The work is force times distance. So force is 200, distance is 10, you get 2,000, but divide by 2, because that's the time, you get 1,000 watts. And remember, a watt is a joule per second. So once we get the joules in seconds, you're pretty much straight there. Next up. If a rubber ball is moving at a speed of 5 meters per second, hits a flat wall, and returns to throw also at 5 meters per second, remember, magnitude doesn't involve direction. They're going to have the same momentum because you have the same mass, because you're talking about the same object. So it stays the same. That's conceptual. This here, some people had a little bit of a tough time with this question. The first 4, I think, were fine. Now remember, your arms are doing the work. So your arms are lifting the books up, or has to be doing some sort of lifting. That's why it's going to be picking up a heavy sack from the floor. Dropping it, who cares? You're holding it, but you're not moving it. Your arm's not moving any distance, right? So dropping or holding, forget about it. Walking is interesting, but remember, it's the rest of your body that's maybe like the legs or something that are doing the work, not your arms necessarily. So your arms are doing the work as you're. Go ahead. I'm sorry, was there a question? No question? Okay, we'll keep moving. Impulse. It's a change of momentum, so that's easy. So I think we're okay there. This diagram. Now remember, your potential energy is going to be high when you have greater heights, right? So that means that when potential energy is high, the kinetic energy is low. So you have to be very careful here. At point C, they said kinetic energy at point C is less than kinetic energy which are following points. So you want to see where else we have a higher kinetic energy than C. Well, the kinetic energy is going to be low at A, D, and E because the potential energy is high there. Remember, the potential energy is high when you're at a greater height, which is counteracting the kinetic energy. So kinetic energy is actually low at A, D, and E. But kinetic energy would be high at B because B has a very low potential energy. So again, at which the object kinetic energy at point C is less than kinetic energy at which of the following points, just be at B, because B has a higher kinetic energy due to low potential energy. If you did say A, D, and E, then you got it mixed up. I'd probably give you a point at least, because at least you were kind of thinking in the right way, but you got it mixed up. I did try to go back and help you guys with partial credit, just so you know. And if you didn't submit work, I think there was probably a couple of you guys that could have benefited. I think I emailed you, so make sure you show me so I can help you out. This one here, during a certain time interval, a 20 object free falls 10 meters. What does the object gain? Well, if you think about it, you're looking at kinetic energy, so it's 1/2 mv squared. So you have to do a little bit of work here. So your remember, force, or your weight due to gravity, is going to be mg. So 20 newtons. Your mass is we don't know. and gravity will assume is 10. So your mass would be 2 kilograms. If you're free falling for 10 meters, you could actually just, if you think about it, you could solve for the velocity. So you could do all this work. You could say, trying to think of the right equation here. I am going to show you an easy way for doing this one too, so in case you're wondering. The initial velocity, say, is 0, plus 2 times 10, so assume 10 for that, 10 for that. So your v squared is going to be 200. So of course you just get 200. Now, could you have just done this also? Sure. Because remember, your work is going to equal kinetic energy, or your work could equal 1/2 mv, the change in the kinetic energy. Because initially your kinetic energy was 0. So you could just done force times distance, and that would get you the same thing as well. I'm just trying to show you how the kinematic equations can back that up too. So you should have got 200 for that one. Keep moving. Yeah, if you're throwing a ball or kind of this heavy ball, towards the back, so what's going to happen is that the mass of the system actually doesn't change. And you're also, you're really at rest, right? So you're not going to see any movement whatsoever. So it's not like you're seeing a transfer of mass. I mean, yes, you are. One person getting more mass than the other, but because there's no initial momentum, there's no movement. You can kind of expect that for the final case when you move the ball from one person to the other. So yeah, there'll be no change in momentum whatsoever. And no movement. We'll keep moving. No pun intended. All right. Now here I have to do a little bit of calculation. So you have a 0.475 kilogram ball thrown horizontally at 12 meters per second. Something struck by a bat, caused in reverse direction, 8.5 meters per second to the right. The bat produced an average force of 12.5 newtons. So this is going to be dealing with impulse, right? Remember what impulse is. That's change momentum. So your impulse is force times time. Because that will give you the same units for momentum. And then you have mv final minus mv initial. So the things that the ball goes in the reverse direction. So your mass, of course, is 0.475. We'll say it's negative 8.5 here. Minus 0.475 again for the mass. And times negative 12. Sorry, times 12, because 12 is the positive direction. And because the force, the bat's going in the opposite direction of the ball. So here's the picture. Throwing the ball this way, we'll call that the positive direction. And here's like home plate, and here's the batter with the bat, and that'll be the negative direction. So the force is also in the negative direction, because going opposite the path of the ball. So that's going to be negative 1275 times time, and that's what you need to work out. if you do that correctly, I believe the answer is 7.64. We can actually compute that really quickly here. So if I do 0.475, that's actually times 20.5, because you're going to combine the 8.5 with 12. And if you 1275 divided by that number, oh, but I have to times, shoot, wait. Something's a little off here. Let me try this one more time. Give me 1 sec here. Force times time. Milliseconds. 0.475 kilograms. Let me come back to that problem because that one seems a little off here. We'll move on. This one is going to be 1 over root 2. And the reason why is that say this astronaut, this ball here and drops it. So right now this is 100% potential energy. When you get down here, of course, it's 100% kinetic energy. So in the middle, we're halfway through, we expect 50% potential energy and 50% kinetic energy. Let's actually be hypothetical. Let's say this was dropped 100 meters. So potential energy would be mgh. And let's say the mass of the ball was 1 kilogram. And let's say that the gravity is like 4 meters per second squared on the moon. So it's 1 times 4 times 100. You get 400, right? Now the kinetic energy, we'll worry about that later, but this is the total energy I have right now. So when you have 50% kinetic energy, that's going to be half of that. So 1/2 mv squared equals 200. And if you work it out, mv squared equals 400. Remember, m is 1. So again, we're being hypothetical with numbers here. So your v is 20 at that point. But with 100% kinetic energy, you're doing 1/2 mv squared equals 400, 100% of the energy from before you dropped it. Remember, m is 1, so v squared equals 800. So v is going to be root 800. Or in this case, it'll be 20 root 2. Because you factor out 400 is a factor of 800, and square root of 400 is 20. You can see how that is 20 root 2 divided by root 2. So it's off by a factor of root 2. That's why the answer is B for that one. So that's how you can prove it mathematically as being hypothetical. You can get a little more abstract and just use like all the, you could say 1/2 mv squared or 1/2 mv1 squared equals 1/2 mv2 squared. But you would need to know the relation between V1 and V2. And of course, we know that it's half the energy. So I guess you would have to half of a half. Those cancel, those cancel, those cancel, those cancel. So V1 squared is 2V2 squared. When you square root, V1 is root 2 times V2 squared. So you could have done it that way also to kind of see the relationship between the two. But that's how that one works. Here it was all three. Remember, potential is MGH, so all three of those can impact your potential, your gravitational potential energy. So it's all three of them. Next up is kinetic energy. Kinetic energy, remember, we know is 1/2 mv squared. Now the position doesn't matter so much because you're, you know, if you're staying on a level surface, your kinetic energy, if you were like, you know, 10 feet above a certain surface or 20 feet, it's all going to be the same, so the position doesn't matter. At that moment, the only thing you're looking at is the mass and the speed. And plus, I didn't really say that if what does position mean? Does it mean vertical, horizontal? You know, if you're looking at change of horizontal position, big deal, it doesn't matter. So it's just M, mass and speed for that one. This one, if two things stick after they collide, so your initial momentum is going to be 0.4 kilograms times the speed. And there's only one thing moving right now, the koala bear, not the clay model. But then they stick together, so now their combined mass is 1. You want to try and find its new its new velocity. So that's 0.1, and when you multiply that out, so new velocity should be 0.1. So you should got, and I said do put the leading 0. If you didn't, you put just decimal 1, I still gave it to you, but just 0.1. Should be a pretty basic conservation momentum question there. Here, yeah, this required a little bit of careful thinking. So remember, the air resistance is working, we're gonna say it's working against you. So right now, we're looking at conservation of energy. Remember, we talked about this. The initial kinetic energy plus the initial potential energy plus your non-conservative work is going to equal your final kinetic energy plus your final potential energy. Initially, you don't have any kinetic energy. Potential energy, your mass is 4. We'll use 10 for G. Your height's 40. Now, the work, because this is going against you, it's going against potential energy, so you consider it to be negative. So force times distance, you can do negative 20 times distance traveled, which is 40, of course. And it's all kinetic energy at the end, so it's 1/2 times 4, and then trying to find the speed, so we'll call it v squared. So that's going to be 1600 minus 800 equals 2 v squared. 800 equals 2v squared. V squared is 400. V is 20. Now, with an elastic collision, First of all, when you have a collision, we're conserving momentum, so you definitely need to conserve the momentum. Because it's elastic, K is also conserved. And things if K is going to be conserved, momentum is going to be conserved also. So it's not like you just conserve the kinetic energy. You're conserving the momentum as well. If you're conserving the kinetic energy, so it's going to be both. This one, I remember the answer was 54. So remember, trying to find how much work was on the object during this time. So remember, force times distance. Your mass is accelerating. So you do need to find the acceleration first. So remember, force is NA. So it's 4 code, and then find your acceleration. That's your change in velocity over time. That's easy. 6 minus 3 over 8. 3/8, which becomes, I think, 1.5 newtons. And then your distance you travel, so remember, we do have a formula for that as well. V squared equals V0 squared plus 2A times x minus x0. You're changing position. So initial final velocity 6, initials 3. Remember, 3/8 is our acceleration. Work all that out. You have 36 equals 9 plus, that's 3/4, or 0.75. 27 equals 3/4 times x minus x0. When you move things around, you should get 36 on the other side. So that's your actual displacement. So you're doing 1.5 newtons times 36 meters. And that's why you get 54 joules. So that's why it's important to show your work to me. In case you missed it, I can see if you made any errors along the way, but and I gave you a hint, you had to use 2 kinematic equations here. Definitely one for acceleration and one for displacement. And remember, force times distance, force. So I gave you all the formulas you need, you just had to use it all. So that's how you would see 17 through. And that's a great problem because it really incorporates everything done the last 3 weeks. I would say this is a good final exam problem because again, it just encompasses so many things here. Keep moving. 18, I do give you the assumption for the acceleration due to gravity. So it's sliding down. So this is conservation of energy. Again, your initial kinetic energy plus your initial potential energy. Is going to equal your final kinetic energy plus your final potential energy. So remember, at the top, you have 4 meters. So your MGH is going to be 3 times 10 times 4. You have no kinetic energy in the beginning. And then your final kinetic energy is going to be 1/2 mv squared, so 1/2 times 3v squared. You have no potential at the bottom. So 120 equals 3/2 times v squared. Work it all out. V squared is 80, v is roughly about 9. That's why you should get 9 meters per second. Now, one thing I'm just realizing right now, which I kind of goofed here, and I probably should have stated this, is that we are ignoring the work due to gravity or due to weight, because that is a non-conserved work. The things I didn't give you the angle for the incline or any other dimension, so you wouldn't know what the this would have been anyway. But to have done this problem more properly, you would have to calculate the parallel force or the parallel weight and multiply by the distance it travels and subtract it. That's what I should have done. So I probably should have said, as an assumption, we're neglecting the work due to gravity. So more thing about this problem is a bit flawed. So if you did miss it, maybe I might come back and give you a little more points, but what I was trying to get, and I should have stated that, we were neglecting the weight due to gravity. Okay, the home stretch here. Find average strength of this force, so we're going to use impulse momentum equation. So you're given the time, so force times time, or 0.5, equals your change in momentum. So that's 2 times 8 minus 2 times 4. That's going to be 8 when you work that out. Your force is 8 over 0.5, you should get 16 newtons. That's a pretty straightforward one. Still don't know what happened to that other problem. Going all the way back here. Yeah, this one. I'm still a little confused why, no, not that one, hold on. Yeah, that one. Yeah, I need to figure out what I'm doing wrong with that problem, because it's supposed to be just impulse one, but I'm sure when I look at it, I'll probably figure out what I did wrong. So let's go to the last problem. Okay, 20. So this actually came from our problem sets, just so you know. So I'm doing a lot of problems that are from our problem sets. In fact, if you click on it right here, it's right there. But of course, I change the numbers around, right? So now there's several things at play here. What's happening here? Well, first off, we have this kinetic energy initial plus potential energy initial plus your non-conservative work equals your final kinetic energy plus your final potential energy. Now, initially, this guy does have speed. So 1/2 times 100 times 20 squared. There's no potential energy, this person's on the ground. We'll come back to this in a sec. I'm gonna leave a little space for that. Final kinetic energy, well, I want to find the final speed, so I am interested in that. So 1/2 times 100, we'll call it times v squared. The final potential energy, that's going to be pretty easy because I know the mass is 100. I know to use 10 for gravity. And of course, the height's 2.5. So that's not too bad. This is kind of the interesting part. Before we get there, remember, force due to friction is going to be mu k times your normal force. Now, when the skier is right here, his normal force goes in this direction, right? Which is going to totally counteract the perpendicular weight. We'll call it weight perpendicular. And remember, your weight, if I draw the incline like this, and we'll say we'll do a crate or a box for the skier, the weight's going down that direction, so that's your perpendicular weight right there. Your angle's right there. So the perpendicular weight is going to be the weight, which we know is 100 times g, or 100 times 10, times the cosine of 35 degrees. And you already know mu k, which is 0.1, and then that's times 100 times 10, so it's times, yeah, I could do that, times cosine 35 degrees. Because now my screen's cracked, that's why it doesn't show. So if you work all that out, look at my cell phone out here. Okay, excuse me. So it should be actually 1,000 times 0.1 or 100 times cos of 35. So I get 81.92. So it should be 81.92 units. That's what you should put right here. Now, let's talk about the non-conservative work. Definitely the work due to friction, because it's counteracting your movement, but also it's going to be excuse me, the work due the parallel, or the work due to gravity. We'll call it WG. Now it's a little confusing because this W is different than W down here. The W down here was weight, just as a force. These W's are more like energy. And actually, it's working against us. You're going to have to subtract it. So the work due to friction is easy. Now you have the force here, right? So if I come and bring this down here, that's 50 times 400. That should be 20 thousandths, I believe. Yeah, 20,000. Minus, now your work due to friction is going to be the force due to friction times distance it travels. So you are going to have to do a little bit of trig here as well. So if that's 2.5 and that's 35 degrees, you do need to know the distance it travels. So you will need to say, if you call it like x, for example, sine 35 degrees equals 2.5 over x. If you solve for x correctly, so you're going to do 2.5 over sine 35, you get 4.36. And the parallel weight will be this mass times gravity times now sine of 35 degrees. So you can also consider that too, because that's also work that's going against you. And if I do that one, 1,000 times sine 35, I get 573.58. And times distance that travels, because it's also going down that incline, or up that incline, 4.36, equals this right here, which is 50v squared. This right here, which is 1,000 times 2, so plus 2,500. And then at this point, you're just doing the algebra. If you do it correctly, 81.92 plus 573.58 times 4.36. So you're doing 20,000 minus that. And then you're bringing the 2,500 over. Then you divide them by 50. So v squared equals about 292.84. And if I square root that, I get about 17.11. Or put 17.12, I gave it to you. But that'll be your final velocity. If you neglected, like to use this or this, but everything else looked fine, I pretty much gave 7 out of 8 because I want to make sure that I respect the work you're doing for this stuff. But yeah, you have to show that though. There's two non-conservative energies or work happening here. The work due to friction is working against you, and you also have to consider the gravity as well. So that was that one. It was kind of a behemoth of a problem. Right, so that covers the whole test. So you have this as a video. I strongly recommend actually all the test solution videos. That might be a great way to study for our final, which will be in 2.5 weeks. I'm going to talk more about that probably after the 4th of July holiday. I'll let you know more how that's going to look. But yeah, I definitely want to do a final exam in some way with you guys. Okay, so let me go ahead and stop the recording.